everybody. This would be lesson 2-1, Connect Ratios, Rates, and Unit Rates. In this lesson, we are going to focus on the I can statement right here on your paper that says, I can use ratio concepts and reasoning to solve multi-step problems. In 6th grade, you learned about ratios, rates, and unit rates, so much of what you see in this lesson may be a review. Let's take a look at the Explain It question first. In a basketball contest, Elizabeth made 9 out of 25 free throw attempts. Alex made 8 out of 20 free throw attempts. Janie said that Elizabeth had a better free throw record because she made more free throws than Alex. And then you can see right here we've got a scoreboard, and the scoreboard shows us about Elizabeth and Alex and the number of free throws that each of them made. So we have a couple of things to consider here. One of them is critiquing Janie's reasoning. Do you agree with Janie? And I want you to explain why or why not. In part B, we're going to look at arguments and constructing an argument. Decide who you think had the better free throw record and justify your reasoning with mathematical arguments. Pause the video for just a few moments while you consider these two questions. In the first question, we really should look at Janie's reasoning and compare ratios for Elizabeth and Alex. Elizabeth made 9 out of 25 free throws she attempted. Alex made 8 out of 20 free throws that he attempted. So in reality, Elizabeth did make more shots. She made 9 and Alex made 8. But she also attempted more free throws than Alex. And she actually attempted 5 more free throws. She took 25 than Alex did. He only took 20. So Janie's reasoning might be accurate in terms of the number of free throws taken, the number of free throws that Elizabeth made, but is she correct when you compare these two ratios? So that's something for you to think about. So are those ratios equal, or how can we compare them? That would help us agree or disagree with Janie's reasoning. In part B, we are to decide who had the better free throw record and justify it using a mathematical argument. In other words, we need some math to support that decision. So go back and look at your answer, or what you have in part A now. Is there a way for you to decide who had the better free throw record? One thing you might consider doing in part B is comparing ratios that have an equivalent denominator. In this case, Elizabeth made 9 out of 25 free throws, which is an equivalent ratio to 36 out of 100 if we take both parts of her ratio and multiply by 4. For Alex, he made 8 out of 20, which is equivalent to 40 out of 100 if you multiply both parts of Alex's ratio by 5. So while Elizabeth made more shots out of the ones that each Alex and Elizabeth took, when you look at their record of what would be expected if they each took 100 shots, Alex's free throw record may be more accurate. Just some things to think about as we go through this lesson. Looking at the top of your page, you'll notice that we have an essential question. This is what we'll focus on during this lesson. How are ratios, rates, and unit rates used to solve problems? So take a look at example 1. In this example, we're going to work on finding a unit rate. Okay? Nathan and Dan were both hired as lifeguards for the summer. They received their paychecks for the first week. Who earns more per hour? So in this case, we're going to decide who has the better rate or pay per hour out of Dan and Nathan. So look at their earning statements. Dan, right here, worked a total of 9 hours and he got paid $78.75. Nathan over here, worked only a total of 5 hours, and he made $46.25. So while it's easy to see that Dan made more money than Nathan for that paycheck, you do notice that they worked a different number of hours. So the way we determine who earns more per hour is to figure out what is the pay for just 1 hour of work. So the one way that we can do that is to draw a model. In this case, we have Nathan's pay and we have Dan's pay, and they are written here as a ratio in terms of dollars on the top and hours on the bottom. Same thing here with Dan, dollars on the top and hours on the bottom. And what we want to know is how much do they each get paid for 1 hour of work? And we do that by dividing the top number, $46.25, by 5, and the bottom number also by 5, because what our goal is to figure out what is the pay, or what are the dollars, when the number of hours worked is just 1. And we're going to do that both for Nathan and for Dan. And what you find is that Nathan earns $9.25 per hour, and Dan earns $8.75 per hour. Okay, which means Nathan earns 50 cents more per hour than Dan. Now let's take that strategy and apply it to a new question. Look at the try it at the bottom of your page. Jennifer is a lifeguard at the same pool. She earns $137.25 for 15 hours of lifeguarding. How much does Jennifer earn per hour? So what we see here is a similar ratio that we had up at the top of the page. Her paycheck was $137.25 for those 15 hours of work. We're going to take that paycheck, $137.25, and we're going to divide by 15, because I don't want to know how much she earns for 15 hours. We already know that. That's her paycheck. I want to know how much does she earn for just 1 hour of work. So pause the video while you calculate her hourly pay, and then unpause the video to determine if you got the correct answer. Jennifer's hourly pay is $9.15 per hour. The convince me at the bottom asks us to basically summarize what we just learned. What do you notice about the models used to find how much each lifeguard earns per hour? So in all three cases, for Nathan, Dan, and Jennifer, what did we do to find the amount that they earned per hour? And the answer is we divided. So we divide the total by the number of hours worked. We divided the total dollars by the number of hours worked. Now let's take a look at example 2. When example 2 shows up here, we see that we're going to be using these unit rates that we just found in example 1 and doing something else with them. Brian agrees to watch his neighbor's dog for 7 days. His neighbor provided a 128-ounce bag of dog food. Does Brian have enough food to feed the dogs all 7 days? Explain. Well, let's take a look at the picture, because that's where the information is that we need. We see we have Buster and we have Roxy. And here is the amount that Buster eats in 2 days, and here is the amount that Roxy eats in 3 days. So the first thing that we're going to do is determine how much does each dog eat in 1 day. So here's Buster and here's Roxy, and we're going to do that division to find out the amount that they eat in 1 day. So Buster eats 20 5/10 ounces, or 20.5 ounces, in 2 days. If I divide that by 2, then I'll get the amount that Buster eats in just 1 day. So here's my Buster eating in 1 day right here. That's the 10 and 25 ounces. If I multiply that by 7, then that will tell me how much Buster eats in all 7 days, 71 and 75 ounces. Now let's do the same thing for Roxy. Roxy eats 22 and 5/10, or 22.5 ounces, in 3 days. So if I divide both of those values by 3, it will tell me how much Roxy eats in just 1 day. But again, I don't want to know how much she eats in 1 day. I need to know how much she eats in 7 days. So I'm going to multiply that by 7, and I get she eats 52 and 5/10 ounces in 7 days. In order to answer the question, though, we have to go back and determine if Brian has enough food to feed the dogs for all 7 days. And remember, his neighbor gave him a 128-ounce bag of dog food. So if we take the amount that Buster eats and we add to it the amount that Roxy eats in all 7 days, then our total here, 124 and 25 ounces, is less than the amount of food that Brian has, so he does have enough dog food. In fact, he'll have just a little bit left over to return to the neighbor at the end of the week. Example 3. This time, let's compare using those rates. Suppose that each jump covers the same distance. You see that we have a rabbit here, and each jump covers the same distance. Then we also have a kangaroo rat, and each of his jumps also covers the same distance. How many jumps does it take each animal to cover the same distance? So if we make tables of equivalent ratios, we can count the number of jumps and how far that animal goes until they get to the same number of meters. So the rabbit takes 3 jumps, 1, 2, 3, and goes 8 meters. That's the first row of the table. The kangaroo rat takes 1, 2, 3, 4, 5 jumps and goes 12 meters. If I continue with the pattern for the rabbit and the kangaroo rat, what we find is that 24 meters is the magic number. That's where they both will cover the same distance. So here's my same distance right here. That same distance is 24 meters. Okay? Now the question is, how many jumps did it take each of those animals? Well, the rabbit, in order to go 24 meters, has to go 3 times that distance. So the rabbit has actually jumped 9 times. The kangaroo rat, however, jumps 5 jumps every 12 meters. So if I double that, then I can see that he has jumped 10 times to get to those 24 meters. So who had to take more jumps to get 24 meters? The kangaroo rat took more jumps. Now let's complete the triad. A kitchen sink faucet streams ½ gallon of water in 10 seconds. So there's a ratio. The bathroom sink faucet streams 7/500 gallon of water in 18 seconds. Let's make a table of those two ratios. Now the question here is, which faucet will fill a 3-gallon container faster? So what we're looking for here is to get ratios that for both the kitchen and the bath have a 3 in the gallons. And then we're going to compare the number of seconds. So let's start in the kitchen. If the gallons is 0.5 or 5/10, which is a half, in 10 seconds, if I double that or multiply by 2, then I get 1 gallon in 20 seconds. And then what do I do to get from 1 to 3? Well, I multiply by 3. So 20 times 3 is 60. So the kitchen sink will fill 3 gallons in 60 seconds. Now let's take a look at the bath. Again, we're wanting to get to 3 gallons. So how do I take 75 hundredths and turn it into a 3? Well, maybe that's jumping a little bit too far, so let's go back. Let's make another row of this table as well, and let's do the same thing that we did before. Let's take the gallons and double it. So what is 75 hundredths times 2? And you get 1 5/10. So I need to do the same thing to the number of seconds. 18 times 2 is 36. Now can I go from 1 1/2 to 3? And the answer is yes, I need to double it again. So I'm going to do this times 2. So that means I'm going to do 36 times 2 as well. And 36 times 2 is 72 seconds. So the bathroom sink will fill 3-gallon bucket in 72 seconds. And the question is, which is faster? In other words, which bucket is going to fill first? In this case, the answer is the kitchen, because it takes fewer number of seconds to fill 3 gallons. The key concept in this lesson has us looking to find those unit rates and then use them to compare ratios and to solve other problems. The key idea behind all this is finding that unit rate, or when the denominator of your ratio is equal to 1 whole. And the way that we do that is we look at the denominator of the original ratio, and that becomes the number that we're dividing both parts of the ratio by in order to get that 1 in the bottom. Remember, any number, like 7, divided by itself is equal to 1. Now I'd like for you to try questions 2 and 4 through 13.